Alright, so this is problem 55. Here we have a diagram of a pulley system with blocks 1, 2, and 3, and the smaller pulley system and the large pulley system as a whole. So what we did first was we drew 4 free body diagrams with 3 of the different blocks as systems and the smaller pulley system as its own system. And for the first diagram, or the first block, the only forces acting on it are the force of tension of the string in this system and the force of gravity. And we say that it's accelerating in a certain direction, and we call that A1. And for the second block, which is also in the smaller pulley system, the force of tension 1 is also acting on it because the same string is connected to it as for block 1. And the force of gravity is also acting on this block. And because it's on the other side of the pulley system, the smaller pulley system, we'll say that it's accelerating in the opposite direction as block 1. So we'll say that it's negative A1. And for the block that is on the right side of the large pulley system, we have a different string acting on it. We'll call that force T3 and force gravity acting on it. And as a whole, it's accelerating at a rate of A3. And our sign convention for these three are all downwards. Oh, for positive. What's up? Dude, don't say that in the video.
It's supposed to be upwards.
Oh, it's upwards, yeah. Upwards. Alright, and lastly we have the free body diagram with the entire small pulley system as its own system. And we'll say that force T3 is also acting on it because it's the same string as block 3 for this large pulley system. And force of gravity is acting on it as well, but force of gravity here is going to be equal to force of gravity on 1 and force of gravity on 2, since that in the system consists of a weightless pulley and these 2 blocks. And as a whole, we'll say that it's accelerating at a force of at a rate of AT1.
The next step is the force diagram.
All right.
So we have our mass.
Dude, yeah.
Okay. So after setting up our free body diagrams, we can write our acceleration statements before we go to our sigma f statements. So for the acceleration of the first block, as we mentioned before, that can be equal to the acceleration of t1 plus the acceleration of a constant k. And we can say that constant k is the difference between the acceleration of t1 and the acceleration of the whole block 1 from the weightless pulley that we mentioned before. And with that, we can start to write out acceleration statements for the other blocks. So for example, as we mentioned before, the acceleration of block 2 is just really the acceleration run of the block 1, just in the opposite direction. So for the acceleration of block 2, we can write negative AT1 minus AK, which is really just the difference of acceleration of block 1. And we can go even further by saying that the acceleration of block 2 is also equal to the acceleration of block 3 minus AK. So by writing all these statements, we see that really the acceleration of these blocks are really just dependent on the direction in which they go, and can largely be equated to each other. And even further, we could say the acceleration of block 1 is equal to the negative acceleration of block 3 plus acceleration constant k. So if you set your acceleration statements correctly, then writing your sigma f statements becomes that much easier.
Alright, so we have our 3 sigma f statements right here. We have our first one, which is just the force, mass 1 times acceleration 1. And as we mentioned before, acceleration 1, we can set that equal to the acceleration of this whole system right here, plus a constant. So we just say that that would be AT1 plus AK, which is the same thing as AK minus A3, because the acceleration of this system is the opposite of the acceleration of the third block. So we say the summation of the forces in the y direction for the first block is just m1 times AK minus A3, which should be equal to the force of T1 minus the force of gravity. As we see by our free body diagram over here, Ft1 minus force of gravity, so Ft1 minus mg. So So this is our first sigma F statement, and this is the first equation we're going to use. Then we have our second sigma F statement, M2A2. And this is the same idea. We just say that we plug in for the acceleration of A2, which is right over here, A3 minus AK. So we have the mass of the second block times A3 minus AK should be equal to the force T1 minus the force of gravity. And we can see that by our second free body diagram over here. Force T1, force of gravity, plug in right here, and we have our second equation. Our third summation equation is just M3A3, and this is simply equal to Ft3 minus mg, as we can see over here. Ft3, force gravity, so Ft3 minus mg. And we have a fourth equation, which is 2 times the force T1 is equal to force T3. We know this because we have our two FTs over here, FT1, FT1. These are both equal to FT1 because they're part of the same string, and FT3 is over here. And these must be equal because they're part of the same larger system. So the two forces of FT1 should be equal to the force of T3. So if we draw a free body diagram for our large system, it looks something like this.
So small.
Sorry. We can say that FT1 is going up in this direction, and there's another FT1 going up in this direction, while there's an FT3 going in the opposite direction because they're part of the same pulley. So yeah, this is the setup. After that, you just plug in and do a lot of algebra. We won't show that because it's very tedious. Good luck, guys.
Yeah,
and that's how you do problem 55.